farther. We're going to go from Earth to space now. And so our next panel is going to come up here. Join me on the stage. And while they're coming, I'm just going to take my prerogative because I'm going to let Dave Charbonneau, who's my colleague from the astronomy department, he's a professor in the astronomy department and also a Harvard College professor here at Harvard University, which means he's an exceptional teacher, which you're going to see how great he is in just a few minutes. But I'm going to take my prerogative to ask him a question before he actually starts. And it's about clarifying what we mean today by the undiscovered. And so I'm just a tiny bit older than Dave, so that when he was a graduate student here at Harvard, I was actually on the committee that decides whether or not students can do particular projects for their PhD thesis. And some of you may know that Dave is extremely famous for having discovered the first so-called transiting exoplanet, which means a planet that passes between us and its host star and makes the star go a little tiny bit dimmer by like 1/1,000,000th of its light. And the technique that he used to do that was something that should absolutely work. Okay, but nobody had ever made it work. But everybody knew that it would work, maybe, someday. Okay, in other words, it was not undiscovered, it was undiscovered. So in other words, it was sitting there waiting to be discovered, but it wasn't a technique that you wouldn't think would ever work. It just hadn't worked yet. But then the planets that were found around other stars are every variety of bizarre, which is what you're about to hear about in this session. And so for you, Dave, I want to know whether you consider, you don't have to answer now, later, but your original discovery as undiscovery or just plain discovery by the almost traditional scientific method. So I'll just leave it there and turn it over to Dave to introduce everyone else in the session. Thanks.
All right, so if you look at the written record of human thought, it's pretty clear that for at least 500 years, and arguably for 2,500 years, humans have wondered whether there were other worlds that were inhabited and that whether or not we could somehow come into contact with those worlds and explore them. And what I want to begin by saying is that this is a very special moment in human history where we're going to do something very special, which is that we have, for the first time, the technological ability to actually go and answer that question. And so there's a great deal of excitement worldwide amongst astronomers and astrobiologists that really within the next 10 years we might detect the presence of life on planets orbiting other stars. And so we're going to talk about these exoplanets here today. We have two of the world's experts and leading thinkers on this really great question. Our second speaker is going to be Professor Lisa Kaltenegger, who is the director of the Carl Sagan Institute at Cornell, where she's also a professor of astronomy. And there are few souls on this planet, at least, who have thought more deeply and for longer than what it would really take to infer the presence of life through telescopic observations. So among many of the exciting questions that Lisa has investigated are, what would the Earth look like to an alien astronomer? And how did the Earth's appearance change to that alien astronomer as a function of time? The Earth has not always appeared as it now does. Could we detect the presence of geological activity, like volcanoes, if you were a remote astronomer gazing across the vastness of space? And which stars we should begin by looking at as we go and do this exploration with our telescopes. Our first speaker, though, will be Laura Kreidberg. And Dr. Kreidberg is a junior fellow in the Harvard Society of Fellows. And maybe to set up a bit of a juxtaposition for the purpose of this talk, whereas Lisa is the theorist, Laura is the observer. And Dr. Kreidberg is really a world leader in using novel techniques and pushing observatories to achieve unprecedented levels of precision to go out and actually figure out what these planets are made of and what are the properties of their atmospheres and whether or not they are anything at all like that of the Earth. And so I'm very excited about this discussion, and I'm going to call on Dr. Kreidberg to lead us off.
All right, thank you, everybody. It's my pleasure to be here. I have the honor of speaking about a topic that really ties together all of the themes of today, which are life, the Earth, and space, which is the question of, is there life elsewhere? And as Dave said, humans have been thinking about this for a long time. I would guess, before recorded history, humans have been thinking about this. But the place I'd like to start is in the early 1960s, when an astronomer named Frank Drake developed the first scientific framework for talking about the possibility of detecting inhabited planets in the galaxy. And so he wrote down this famous equation. Looks like it's not there. Well, I'm not allowed to have equations in talks anyway, so that's fine. The way Frank Drake thought about this was he started by saying, okay, well, how many stars are in the galaxy? Presumably you need the star as a source of energy for your life. And then he said, how many of those stars host planets, in particular planets that are likely to be habitable? We'll come back to that later. And finally, how often does life actually arise on those potentially habitable planets? And if it does arise, can we detect it? And so the goal was to get a number of potentially detectable and habited planets in the galaxy. And this all sounds fine. It's a very organized way of thinking about it. The problem was that in 1961, nobody knew what any of these terms were. And the way it was approached was the way we were all taught as young scientists, which is to develop a hypothesis and then try to figure out an experiment you could use to test that hypothesis. And so if your hypothesis is that there are other stars in the galaxy that host planets like the Earth, then your experiment is, can you detect these Earth-like planets? And so folks went through this exercise of trying to figure out how we would go about doing that. And so the most natural first question is to say, can we just take a picture of the planet, maybe block out the light from the star? And it turns out that this is very, very hard. The Earth is 10 billion times fainter than the sun. And not only is it much, much fainter, it's also very close to it. And so the analogy is that this is very similar to trying to detect a firefly next to a lighthouse at a distance of a couple of 100 miles. And so this was ruled out as impossible. Oh, is it going? OK, good. So another idea was to try to search for a transit of the planet. This is when you get lucky with your geometry and the planet goes directly in front of its parent star. And when it does that, it blocks, as Alyssa said, a tiny fraction of the stellar light. The challenge is that for an Earth-sized planet around a sun-like star, it's only 1 part in 10,000 of the stellar brightness that gets blocked. And that was considered also too difficult to detect. Not only is it difficult to detect, it's fairly improbable. Only 0.5% of the time would you expect this chance alignment to work out in your favor. And it only happens once a year. And so even if you did somehow build a detector that could see it, suppose next year you went back to try to detect it again, and if you're observing from the ground, it could be cloudy, it could be daytime. You might not be able to see it at all. Folks also thought about trying to detect the influence of the planet on the star. So planets have some mass, and we normally think of the star as fixed in space, but the planet is orbiting around. But really, the planet's gravity tugs on the star a little bit, and it makes it wobble. And so you could imagine that maybe you could detect that wobble by observing the spectrum of the star, the color. And when the star is moving towards you, its light is a little bit blue shifted, just by the Doppler effect, the same thing that makes the siren sound higher pitched as it's coming towards you and lower pitched as it moves away. And then as the planet moves away, as the star moves away from you, its light would be then redshifted. The problem here is that the size of the signal, the amount of motion induced by the Earth on the sun is only 10 centimeters a second, which was far too difficult for any detector at the time to ever see. And so even though this is such an exciting question, everyone was saying, oh, there's no way, this is too hard. except for a handful of very persistent, very stubborn people. One of these was Paul Butler. And he described what it was like to try to search for extrasolar planets in 1986. And what he said was, when asked by other astronomers, what are you working on? One could not respond, I'm searching for extrasolar planets. Depending on the person, they might laugh in your face or slowly move away from you, like you were pitching an alien conspiracy theory. But nevertheless, they tried, they kept going. And this is an amazing, amazing figure. This is the discovery data for an extrasolar planet that was completely unlike anything that was ever seen in the solar system. So this was from a team of astronomers who were using the Doppler wobble technique, and they measured the velocity of a star called 51 Pegasi. And this is what they saw. They saw these characteristic wiggles that are exactly what you would expect if you have a planet tugging your star back and forth. The crazy thing about this is that the amplitude of that signal was 100 meters per second, compared to 10 centimeters a second for what you would expect for an Earth-like planet. And so I love this quote from a colleague of mine, Emily Levesque, where she said, the real exciting sound in science is not eureka, it's, huh, that's weird. And that is exactly what we're seeing here. So the inference here is that in order to have a signal that large, you have to have a planet comparable in size to Jupiter, orbiting its parent star in about 3 days. And this was considered absolutely crazy. There's no way a planet could form there. We think that the material that goes into forming Jupiter-like planets would all be vaporized at temperatures as high as you would get so close to the star, and yet here it was. And even still, there were detractors. People thought this was so nuts that maybe it was something on the star, maybe it was star spots, maybe it was something else. Until about 5 years later, when Dave, who we're fortunate to have here today, decided, nah, like we have to prove this for real, and went out and searched for transits of the planets. And so I'm glad that Alyssa was amenable to letting him go do this as a graduate student. Yeah. Oh yeah. So this was, not viewed with some skepticism. Is that right, Dave?
There's a whole backstory.
Okay.
But I do like that plot.
And so this was the absolute unmistakable proof that these signals have to be caused by planets. So this was a star that had a detected radial velocity signal. The star was wobbling, and then Dave went out and looked exactly when he expected the planet to transit in front of its host star and saw this characteristic dimming of about 1%. And so this was the push that everybody needed to say, oh, maybe there actually are planets around other stars, and they might not have to be like the planets in the solar system. And so the floodgates opened, and there are now over a dozen searches using both the transit technique and the stellar wobble technique that have been going on for over 2 decades now. And so I'll fast forward to what our picture of exoplanets looks like today. And this is what we found. This is the plot showing the pace of discovery. This is the number of known planets, number of discovered planets detected every year between 1995 and today. There are almost 4,000 of them. We know now that the average star hosts at least one planet, typically. Some have many more. And the diversity of planets is much greater than we ever could have imagined from the solar system. So not only did we see these hot Jupiter-like planets, the very first ones that were discovered, we also see many planets that are intermediate in size between the Earth and Neptune. We have no solar system analog for those planets. We see many, many, many planets on orbits interior to that of Mercury, which is the closest planet to the Sun. We see planets orbiting stars that are very different from the Sun, stars that are larger, stars that are smaller and cooler. And as the excitement about this grew, so did our technological capabilities. And so that original question of, are there other Earth-like planets, suddenly became something that was within our reach. And what we now know is that roughly 10 to 20% of stars host an Earth-sized planet with temperatures appropriate for liquid water on the surface, which is the canonical definition for the places we're most excited to try to find life. And so here we are, we're at this sort of crossroads. Going back to the Drake equation, we now know what a bunch of the terms are. We know that there's about 300 billion stars in the galaxy, that almost all of those stars host at least one planet, and that very, very many of those planets are potentially habitable. And so the question for me is, what do we do about these last two pieces? How often does life develop? How can we go about detecting that life? And there are a couple ways to go about this. We're going to hear later in the afternoon from Jill about technosignatures. I'm going to talk about something a little bit different, which is searching for biosignatures in the atmospheres of these planets. And this is a little bit of a gamble. So I really liked what Stuart talked about this morning about searching for a black cat in a dark room. That definitely feels like what I do in my day-to-day work. But it's not exactly, it's not a bumbling search. We make these guesses to say, oh, maybe the cat is sitting on top of the dryer because it's warm up there. Like, that's where we would expect a cat to normally be. And so when I think about the undiscovered in science, to me it feels a lot like a sort of calculated gamble. I grew up in Nevada, I know about gambling. And so the gamble that I'm taking is to study some Earth-sized planets in the habitable zones of their host stars, but these planets are very, very different from the sun. And that's because they're orbiting much smaller stars that are a lot cooler. And there's a lot of advantages to doing this. We know that small stars are actually much more common than sun-like stars in the galaxy. So this figure shows the sun would be one of these bright yellow circles. These are all of the stars within about 10 parsecs, so very nearby to the sun, and you can see that most of them are quite a bit smaller. Not only are small stars more common, the habitable zone is also closer in, so if you're searching for transiting planets, the transits are more frequent, the transit probability is higher, and most importantly, the planet is much larger relative to the star, and so they're easier to characterize. And excitingly, we've started to detect a lot of these planets. This is so exciting that it made the Google Doodle, which I think is a sign that you've made it as a scientist when your results end up on the Google homepage. So I really identify with the moon in this animation. So yeah, we now know of about a dozen nearby terrestrial planets orbiting these very small stars where we have some hope of studying their atmospheres and searching for signs of life. However, there are some caveats that I should mention, and this is why this is risky, which is that small stars are very, very different from the sun. They are bright in the ultraviolet, so they emit a lot of high energy radiation in their young lifetimes that could be very dangerous to life trying to develop on the surface of the planets orbiting them. It could also evaporate the atmosphere of the planet, so we're not sure whether planets around these stars can even hold on to atmospheres at all. They have powerful flares that could also disrupt the development of life. And finally, the planets are expected to be tidally locked to the stars. That is to say, they have a hot day side and a cold night side, just like the moon is tidally locked by the Earth's gravity. And in this situation, you can imagine that you're not going to have a smooth temperature all the way around the surface of your planet. You'll have a really hot part, you'll have a cold part. You might worry about your atmosphere freezing out on the cold side, so you get a snow cone situation where there's like ice on one side and rock on the other side. And so there are a lot of detractors who argue against searching for atmospheres, searching for signs of life on planets like this. But I think that's silly. And so this is what I do. I'm interested in trying to measure the compositions of the atmospheres. This is a little animation showing how we would go about doing this. And the idea is that when the planet is in front of the star, a tiny fraction of the starlight will filter through the planet's atmosphere, and it can get absorbed by molecules that are present there. And depending on what the molecules are, they have different opacities, different levels of transparency at different wavelengths. And so if we measure the size of the planet, different colors, we can work backwards and figure out what the atmosphere is made out of. And just to illustrate with a more close-to-home example, this is what the Earth looks like in the infrared. That's the moon in the background. And if I move to a different wavelength where ozone is very opaque, it looks like this. You can see these small differences. And so that's what we're looking for in the atmospheres of these other planets. This actually works. This is my one science result that I'll show you. We don't have yet the sensitivity to look at planets that are this small, but this is a planet similar to Neptune, and we detected water in its atmosphere. So those two big bumps are where the planet radius is larger because water vapor is absorbing and blocking the stellar light. And so what we expect is very soon, not with telescopes that we have available yet, but in the near future with James Webb, which is the successor to the Hubble Space Telescope, that we're going to start to be able to make these measurements for Earth-sized planets around the smallest stars. And so this is a result from a paper I wrote with my office mate, Caroline Morley. And we were sitting around and we were saying, okay, you know, we have no idea what the atmospheres of these planets are going to be like. And so to deal with that uncertainty, we said, well, you know, we could use the solar system as inspiration. We have different kinds of atmospheres for the solar system planets. And so here we were like, well, you know, maybe it has an atmosphere like the Earth that has a lot of water vapor in it, or maybe it has an atmosphere more like Venus that is dominated by CO2, carbon dioxide. Or instead it could have methane, which is a situation we see on Titan, one of Saturn's moons. And so we made a prediction for what the signal should look like for these different atmospheres. And we found that this is something we will be able to detect using the James Webb Space Telescope with a fairly reasonable amount of observing time. And so this is something we can look forward to within the next 5 years or so. And normally when I talk about this, I feel like I have to, like I'm on the job market and I have to have some sort of punchline where I say, oh yes, and that like this will tell us that the planet is inhabited or not. And for the purposes of this talk, I'll be honest and say we have no idea. We have absolutely no idea what we will find. But we're trying to design an experiment in a smart way where we can learn at least the very beginning of what kind of chemical inventory these planets might have so we can start assessing whether they host life or not. And so to end, I'll leave you with a quote from Frank Drake. I had the honor of meeting him a couple years ago. And the question I had for him was, knowing what we know now, what do you think the chances are of discovering life elsewhere? And he said 100%. But I'll add the caveat to that, that in order to find that life, we have to keep an open mind about how and where we search. Thank you.
So thank you to Laura for this great introduction to what we're trying to do, what we're trying to achieve. And Dave already mentioned this. If you just take a second to think that we are the generation that might, we have the technological possibility, but we don't know how hard it's going to be to actually spot life if they're unique signatures. That's what we're going to talk about. But we are the first generation in all of humans' history that has to chance to figure out if we're alone in the universe. It's us. I think that is one of the most amazing times ever. And you know, sometimes people pick with when they would like to be born, and I would pick now, all the time, because living in a time where we're gonna get this connection to the cosmos, where we're going to look up at the stars and not just statistically right now say 1, 2, 3, 4, 5, right? 1 out of 5 stars has a planet, small enough, and at the right distance, not too hot and too cold. So maybe, just maybe, that could be also a habitat there. It's potentially habitable. Whether there's life is another complete question. But we have the technological means to actually figure this out. And whatever else you might think is going wrong in our life, this is not one of these things. We are the explorers of our centuries, I would say. And I'm sure it was great for Columbus to actually find the New World, but we have an S on him. We have new worlds, thousands of new worlds that we are discovering. And so, in the context of this meeting, I wanted to add another aspect to this. So yes, in science, with new techniques, and Laura was saying that with new telescopes, we get more detailed and more detailed information. But I like this Charbonneau quote where he actually says, the task is not so much to see what no one yet has seen, but to think what nobody yet has thought about that everyone sees. So what I want to do and what I'm going to try to do right now, so first I'm going to show you a couple of amazing artist impressions to visualize our data. This is one of them. So what you actually have here, hopefully this will run, yes, is just a representation how diverse these other solar systems are. So what you see here is actually, oops, this did not work, okay. Each of these circles represents one of the hundreds of planetary systems that we have detected. And yes, grant you, the planets are not that big compared to the star, but the planets compared to each other are these big dots that go around, and you see some just need a couple of days to go around their star. So if you ever wanted to be older, celebrate a birthday on 51 Pac B. It only has a year from Monday morning to Friday afternoon. Incredibly hot. That Jupiter is evaporating right now because it's so close to its sun. So if you look at it in 1 billion years, it will look different because it will have lost part of its atmosphere. But with more and more observation time, we're finding planets that are more and more in a temperate zone, and especially, as Laura was saying, around these cool stars. Because, of course, stars work with nuclear fusion in the core, but you can think about it as a bonfire. If you have a big bonfire, a big star like our own sun, you have to be a certain distance away to be warm. Too close, you're too hot. But if the star is smaller, you need to be closer in for the same amount of warmth to get to you, radiation to get to you. And so we looked. That's what you should always do in science. And we were looking for patterns. And it turns out that these small stars are the most abundant in the universe. About 75% of all stars are these small red stars. And they tend, or they make, rocky planets incredibly efficiently. So Mother Nature, in a way, did us a great favor for us astronomers and for a search for life in the universe, that where we can actually find planets that could potentially be like the Earth, she made more of them. And so we were off to a very good start because it could have gone completely the other way. And so what I want to talk to you about today is that with all of this, with thousands of planets that we've already discovered around other stars, alien suns, now, what are we looking for? And Laura gave you this beautiful introduction to, well, let's say the whole atmosphere is CO2, right? Then if I look at it, part of the light will be blocked out because it will hit CO2 molecules, and a certain energy will make a certain atom or certain molecule swing and rotate. It has to have a certain energy, thus a certain color. So think about it this way. The light from the star hits the planet's air, gets filtered through it, and then comes to my telescope. So if there are molecules and atoms in this air that the light can hit, that it can strike, less of the light comes out on the other side. So I'm in my telescope, I'm looking at this, and I'm a theorist, but as soon as we find these exciting planets where there are biosignatures, I will also use the data, as Laura is amazing done already, and David. But what I'm just saying is that by what's missing in the light getting to my telescope, that what tells me what the chemical composition of these other worlds are like. And with the next telescopes that we're building, we actually can start to figure out whether or not the small rocky worlds could be anything like ours. But of course, not just ours right now, because the Earth has changed through time. And when I teach this in Astronomy 101, I have a big intro class that I love to teach. And I say, what is the one thing, if anybody ever came with a time machine and said, you can go back to the past or up to the future, what's the one thing you need to bring? And it's usually a camera. I'm like, congratulations, you're opening the door of the time machine, and you did. Because the gas or the atmospheric composition of our planet was completely different when it was young than it is now. We had no oxygen initially, for example. What was going on while the dinosaur worms is different than was going on right now, and probably in the future things will be different too. So I tell them to take a gas mask or their own oxygen plus a camera, because yes, I would like a picture. And no, you cannot make a time machine. Einstein showed that. That's just my theoretical question. But let me bring you back in time a little bit. 41 years ago, we've actually sent out our first message in a bottle, humankind's message to space. That was Voyager 1 with the golden record. And Carl Sagan at Cornell led the team that put together a representative idea of what the music and the art of humankind would be, this message in a bottle. And so we sent this mission out. It had a scientific mission, Voyager 1, in 1977. It went to the outer planets. It told us a lot of exciting science. And then it took a last swing by and basically made its way towards the next star with our message on it and a very cute quote to music lovers everywhere on it, and a description how to build a record player in case some aliens came across it. And I won't say much more because Jill is going to talk more about technology signatures and intelligent life. But to say before Voyager did that, left our solar system, it basically looks back one last time to look at our own world, our home world. That's what Carl Sagan named the pale blue dot, and he wrote a beautiful piece about it. But if you look up here on the right, this small dot, that is us. And he said, everybody who's ever loved, everybody who's ever lived. And he goes in big detail on about this love for this one world, the one world we know can sustain life. And I will go with the session before us. Please let it sustain life for much longer, because we have found other worlds, but we can't tell you if any of them is a good vacation place, and we have no way to get there. So on the flip side, you really don't have to worry about anybody coming here either, because these things are light years away. And so if you take our whole solar system, and it's the size of about a cookie, then the next star, this next alien sun, and the amazing thing, even that one has a planet that could potentially be like ours, is 2 football fields away. So travel is not a possibility yet. However, these worlds teach us. It can teach us also about how worlds evolve in the first place, and when we can start to analyze the small ones, how worlds like our Earth can actually evolve in the future, give us an insight into a long-term future of habitable worlds like ours. So even if you don't care if there's life anywhere else, you kind of should care in the long run what happens to our own planet, hopefully. And that is one of the other answers that we can actually help with, because we have more examples, thousands of other worlds, where we can start to understand the atmosphere and the dynamics. But so if you have this tiny dot, what you'd like to have, of course, is a picture like this. Oceans, continents, clouds, but it's too far away. So what you can do is you can look at the light, and instead of actually splitting out into sectors, this is where there's a coast, this is where the oceans, you can split it up into its light. So from red to blue, for example. And just have a look. It's the spectrum, like a rainbow, right? So basically when there's a raindrop, it splits the white light from the sun in its colors. And then, as I said before, you look and see which colors are missing. And so this should be a smooth curve, but it's really not. And so where there's something missing, it's not smooth, like a bite out of an apple, that tells you where light, the energy of the light was just right to make the molecule swing and rotate. We're looking in the infrared right now. And that's unique because, of course, an oxygen, O2, right, looks different than, for example, an ozone molecule, 3 O's. So a different kind of energy is needed for it to start to swing and rotate. So by figuring out what's missing, you can see here the makeup of the air in our own planet. So you see ozone, you see methane, and water, and also CO2. And the combination of ozone or oxygen, either of the two, with methane, a reducing gas, is the telltale sign for life as we know it. Because we can't produce it with biology alone. Oxygen and methane will react to water and CO2. So if you still see oxygen and methane in the air, what that tells you is that something is producing in huge amounts right now. And for oxygen, we have no other explanation than that being life. So that's our way to say, okay, if you looked at the Earth from far away, this is how you could figure out there's actually a biota, life on it. And this spectral fingerprint, or this light fingerprint, is unique for the planets in our own solar system. What you see here is Venus, Earth, and Mars. And then down here, 2 of the other exciting places in the solar system we're interested in for life, Titan on the left and Europa in the middle here. But how do you translate this? Of course, we can use it as a template, and that's what we study and what we do. But how do you translate that further to a planet that is nothing like, or that's not a carbon copy of planets in our solar system? And this is where the theory of understanding planets and atmosphere, interiors of planets, how they interact with the air, how they interact with the heat coming from the star, comes in our undiscovered, in this idea of this undiscovered box of what could be out there and what we should be looking for. But as a first step, we can just use our planet again as a Rosetta Stone, Earth. We know that it differed through time. About 4.6 billion years ago, it got formed. And if you put this on a kind of a 24-hour clock, if you want, about 3 a.m. is when life started on the Earth. And about lunchtime is when it started to release oxygen in the air. So before that, I don't have a way to identify it. Even though it was there, it only made methane or CO2. And that I can also make geologically. So it's not so much that it's not there. It's more that it doesn't leave us with a unique sign. So in this undiscovered parameter space, we not only have to find worlds that could be like ours, so could host life like ours, we also have to find worlds that we can identify such life uniquely. Because we go with Carl Sagan here again. He said, extraordinary results better have extraordinary evidence behind them. And so this is a view of how our planet changed, again, an artist's impression, of course, but you see from early on to now, and that brought with it a change in biota as well. So intelligent life, I took Einstein for that, so we're going with, we have intelligent life here, but I'm going to wait for Jill's talk and see whether or not she agrees with that assessment. But all this, again, translates into this light fingerprint. Our planet looked different when it was young, it looks different now, and it will look different in the future. But it's something that we can catch with these advanced telescopes that we're building, and it won't be easy whatsoever. And I would like to tell you that it's going to be easy to do with this new 6.5 meter telescope, the James Webb Space Telescope. So it's going to be about 4 times my size in space. What's great? However, it's going to be at the limit of our technical capabilities to find it. And this is, of course, why we need excellent observers like Laura and Dave to make this work, to let us find these features. This is what one of the telescopes looks like. It's one of the extremely large telescopes envisioned to be in Chile. It's a 40-meter telescope on the ground because you have to take out the atmospheric disturbance on the image you collect from the ground, so it needs to be bigger. And this is the telescope, the James Webb Space Telescopes we should be launching in 2021. And while saying that, we have just launched this year an amazing small telescope, the TESS satellite, that is actually not just giving us statistics, because I said count to 5, 1 out of 5 stars has a planet that could be like ours. This TESS satellite that we just launched in April this year actually started taking science data in July, and it's telling you which of these stars actually does have the planets that could potentially be like ours. And it's going to give us our closest travel destination, even so this is going to be in the far future. But in the last couple of minutes, what I wanted to show you is now, this is undiscovered, and this is out-of-the-box thinking that we need to actually find life in different environments. We can use Earth as a Rosetta Stone, but we're basically not just going to use life on Earth like plants and everything you see. We use life in the deep oceans, or we use life like water bears that basically survive kind of everything. They even took them to the International Space Station, put them out, no shelter. 3 days later, they put them back in, put water on, and it was like, da-da-da-da-da, I'm fine, right? So life is incredibly diverse and versatile, even on our own planet. And in our search, we need to put that into our search strategy. We cannot just look for a planet that's exactly a copy of ours, because even with billions of planets in our own solar system, the chances to find one that's exactly like ours right now is probably not as high as you'd like it to be. But if it's just a little bit different, we already know of life that can survive there. So if you, for example, walk through Yellowstone, all these beautiful colors is actually biota that lives in different conditions. And this is just a really funny cartoon. It's like, what do you mean extreme, right? Because what's extreme for us, for other life flights of the Earth, for other biota, is perfectly fine. It's where they strive. So the envelope for what conditions allow for life on the Earth are much bigger than what we usually think about, because we don't think about these extreme forms of life. And so one of my PhD students put together a color catalog of life for going to many, many different places on the Earth, taking this biota and then saying, how would it actually look like if you saw a planet that was dominated, let's say, by an algae bloom or by something else? And it changes the color and probably also the atmospheric composition. So this is, in a way, the undiscovered, and thinking outside of your box, or at least find other people who have different boxes and put all of that information together. And of course, the star also has a huge influence on it. Whether or not that life gets hit by red light or by white light is a different influence in its evolution. And we don't know much about this because we only have our own Earth that was hit by white light. But these small stars, as Laura was saying, are also incredibly active. So what would life have to do to survive, like huge UV on the surface? And Laura was talking about life on the surface, because of course life can shelter underwater or can shelter underground, and it doesn't matter how much UV radiation hits the surface. However, we were trying again to think out of the box in our research, and we're saying, what does life do? What are the different strategies of life if you hit it with a lot of UV? And these are algae that you see here, that when you hit it, actually, it starts to biofluoresce because it lives in symbiosis with algae. The corals start to biofluoresce because they live in symbiosis with algae that can't survive UV radiation. And so it's not to say at all that that would happen on another planet. But it is a strategy that life on a very high irradiated environment could take to actually mitigate this harsh UV environment. And actually, biofluorescence on the Earth we use it. We don't use the corals because there's only 0.2% of all the surface of the Earth that has corals. But this is how we actually judge whether or not plants are healthy. We use fluorescence because plants also fluoresce. Most of the things on the Earth actually fluoresce. And if you go to your next aquarium, it's a little hard to see. Up here, you see these biofluorescence corals. So in most of the aquarium, if they have UV light, these biofluorescence corals are the ones that, if they were to make up these other kind of worlds, if that was an evolutionary path that could work, a really interesting idea would be you'd have this huge flare on the star, and the planet next to it would light up because it breaks down the harsh UV radiation and gives you additional visible light. So the way to think about it, this undiscovered, is also to think, stretch your imagination, because we have this incredibly diversity of worlds out there. And using Earth and all its facets, not just anything we think about every day, as a Rosetta Stone, is our one way to get at least a little bit close to the answer how we could find life out there. And that's my last slide. This is NASA's Artist Travel poster to a planet like TRAPPIST-1. But I love the quote that an author from San Francisco, and he's contemporary, wrote about our survey in the stars. And he says, "One day, from the shores of a new world, we'll gaze at the sea that took us there, and the waves will be stars." And that will be far, far in the future. However, what we're doing right now, these discoveries we're making right now, is enabling humanity, or anybody who comes after us, to take this next adventure. Thank you very much.
Okay, so we can kind of keep this a little conversational. You know, one thing in the theme, I mean, there's so many great things to talk about with exoplanets, but really to get at the theme of the undiscovered, one thing that keeps me up at night as an astronomer is the role of our tools, right? So we use telescopes. That is our tool of choice. And you know, if I think about a lot of the important steps forward in exoplanets, you know, we talked all about atmospheres. The first discovery of an atmosphere was made with the Hubble Space Telescope, which was conceived of and designed and launched before we knew of anything about exoplanets. There was no concept that people would ever use the Hubble for that purpose. Mm-hmm. Similarly, if you think of the first time we measured light from planets, that was done with the Spitzer Space Telescope. Same story again. So, you know, I just wanted to get your thoughts on how, you know, the point is, should we design our experiments to really go and detect something very specific? Or is there a danger, and should we build much more general purpose observatories, but by nature they will not be as penetrating on a particular topic? And what the dangers are of, you know, over-designing tools in a field that is largely undiscovered?
That's a great question. I think that, so someone earlier brought up the metaphor of searching for your keys under the lamp, in the easiest place to look. And I think there's something to be said for that, because there's, like, and that was actually presented as a negative. But for us, observing the atmospheres of these planets that are so small and so far away is so technically challenging that usually my approach is to say, like, I'll take whatever I can get. Like, let's, like, design something that would give us a reasonable chance of learning about the atmosphere of a planet like this, and keep an open mind about what exactly the signal is that we're trying to see. So so more specifically, not just I want to detect oxygen on an exact Earth analog.
Right. But I mean, let me push on that a bit. So, you know, if you know, Lisa, you showed all this kind of great diversity of life on the Earth. The truth is, when we are designing our experiments to go and look for life, we're really looking for life that's identical to that on the Earth. I mean, that it's got to be a rocky planet, it's got to be the same temperature, it's got to have oxygen and methane and water in the atmosphere. And, you know, is is there a danger to basically looking for a mirror of ourselves? And what would it take to go and recognize life that was fundamentally different than life on the Earth? Is that something that we could aspire to do, or are we basically shackled in that we could only ever recognize life that's so similar to the Earth that that's the only thing we can look for?
So I think there's two parts of that answer. And one part is that what we learn from planets is that they are very diverse. So what you don't want to do, what you definitely don't want to do, is basically limit yourself to, let's say, with this one I can find one molecule because I've now put all my eggs in the basket that oxygen is what will define life. Because we'll figure out oxygen you can make by splitting water, right? Or by splitting CO2. So giving you the context is key. And so if you can get as much wavelength as you can, that is your first information, Split the light as far from one side to the other as you can. Get an information on the temperature, plus get a confirmation on the reflected light. However, I think with this big multi-purpose telescope on one side, there is these small explorer missions that are key to our success. Because, for example, if I want to know, well, how much radiation really hits my planet, right? I might not need this huge, huge telescope, but a small, dedicated telescope that does this one just perfectly right, or TESS, basically look in all the closest nearby stars to give me the answer on which of our closest stars have potentially habitable world. I think the key thing in science is that we're developing our tools and we'll always want to have one big thing that can do a lot, but we need to keep it, I would say, wavelengths-wise or energy-wise as wide as we can, and then have this complementary small missions. And the second point that I haven't got to, but very shortly, if I know what to look for, then I can say, this I can only explain with life. I can find other lives. We're looking for things that look weird, right? However, I won't be able to tell you, I know for sure that this is life because we can't make life in the lab yet. So if I'm just, what I mean is like if silicate-based life, right? Carbon has a lot of things going for it, water too. And we're looking at this warm place around the sun, similar to what the Earth gets in energy, only because the idea is that if you have a huge ice layer, like for Europa, if there are gases produced by life, it gets trapped, or it can get trapped under the ice layer and will never make it to my air. And the only thing I can assess, if I can't go there and drill a hole in the ice, is the air. So I'm trying to make my planets be where they're not going to freeze over. Yeah. So I think there are a couple of things that go into this equation.
Okay. So I think what we want to do, this is great. I think what we want to do is ask people with questions to come forward, to make sure to use the microphones. And we'll give you a moment to step up.
Hi, I'm Rachel from Barnstable. So the stars that we're looking at for having life, they're light years away. So technically, we're looking into the past. So should we be comparing our Earth from the past, like in our atmosphere as it was from the past, to those atmospheres? Because it has the potential to change like we have changed over the billions of years. So yeah.
Right. Yeah, and I can see a long line of questions. I see we have 10 minutes. Can we do like 2 or 3 sentence answers? And that way we can really kind of keep it going.
So the good thing we have going for us is the closer a star, the more light I get from it. So I can only see things that are only about 100 years away that have planets around it. But your question is exactly right. We see it like it was 4 years ago. It's the closest star, 6 years, 10 years, 50 years ago. And it could have changed meanwhile. But fingers crossed, they figured out how to do climate change, and we're not going to be too late when we find signs of life.
Thank you.
Okay, thank you. Next.
All right, hi, I'm Liv Eldridge, and I'm also from Barnstable High School. So in sci-fi movies that you see today, you usually see that the aliens are more technically inclined more than we are. So what's to say that we're not the ones that have the best technology and not them?
I think that's a great point. In my mind, there's no clear indication that intelligence is actually evolutionarily favorable at all.
I think I will go.
That's absolutely true.
I think I would go for the other way. Sorry, just a quick question. If there really life everywhere could be, then we talk about 1 in 5 stars. We're talking about 40 billion planets out there. And I have high hopes with stars being older and younger that some of them are going to be further along and some are going to be less along. The question is how long they survived. But I'm an optimist. I think we're going to make it.
I'm Tatiana, also from Barnstable, and I've seen things on YouTube talking about this Great Barrier, and if us as humans, if we've crossed that Great Barrier and we've been able to overcome that, and that's why we've been able to evolve, like, what's your opinion on that? Do you think we've actually crossed that barrier?
I think there's a very fun sci-fi novel there. There's actually a really good one where Reynolds is talking about this, where he says, well, you know, you don't live long enough, so once you at this threshold, then some alien will come and bring you there so everybody can meet. But I said I'm an optimist by training. I think life, the problem is we sometimes think of us, whether we're going to make it, finding another alien civilization and communication with that, I'm not sure. However, that life is still going to be around when somebody else comes looking for us, I'm pretty sure. It takes a lot to kill life on the planet, fortunately. It doesn't take that much to kill us, so we better be a bit careful.
Hi, I'm Colleen Ellis, and you'll never guess where I'm from. So in our astronomy class, we learn about really, really big numbers, and it's a lot of 17-year-olds disassociating and having existential crises at 8 in the morning. How do you as professionals deal with such large numbers day in and day out?
So I think like I teach a class with 250 undergrad students that just coming into Cornell and love my class. And so sometimes they also, so the existential crisis will stay, they're just going to become different. This connections to our stars. Everyone can always look up and you'll see those stars. They're always going to be with you. Nobody can take those away. In the Saharan desert, when you have nothing or when people have nothing else, no TV, no technology or something, they still have the stars. And so to me, it provides me a beautiful context to the universe and how I fit in. And I'm trying to tell them that. And the other thing you can do, it's a really cheap birthday present. Figure out which star is, let's say, 20 years away. Print that out, give it to your friend, cost nothing, and it's a beautiful present, just as a life choice.
Thank you.
And I'll add to that really quick that it's not something you ever really get used to. So I really liked something that Kaylee said this morning or last night about the first time she saw the Andromeda Galaxy, and she said she cried for like 15 minutes. That happened to me when the first time I went observing, and I saw all of the stars in the night sky in Chile in one of the best observing sites in the world. And I had to take a minute to go outside and just sob because it makes it so real how many stars and planets there are. And so the sheer number of inhabitable planets in the world or in the universe is something that you never really get used to.
I'm Alex from Barnstable High School, and do you think that non-carbon-based life forms could exist, and are you looking for them? And another question, do you think that a life form would have to be bipedal to achieve space flight and go to like other another solar system or another planet?
So, great question. Let me answer the second one just very fast. No. Because I think that's more to do with sci-fi movie budgets, and they had to fit somebody in there who had 2 feet and 2 legs. It was cheaper than doing CGI. But the first question is a very good one. What about life that's completely different than ours? One thing to think about it this way is life, as we know it, is incredibly good in using what's around to live, right, or to evolve. So that's mostly when you look at the universe, that's hydrogen, oxygen, and carbon. So for life to actually not use carbon and water, a couple of things would have to happen. So for whatever reason, even chemical, they are favorable. But if you go to a temperature range, like on Titan, where it's so cold that water would freeze, you need another solvent. If life always has like RNA, DNA, molecules, vesicles. The problem is I don't know what to look for. So we're designing our missions for life as we know it. We know it evolved, the case of 1. If we ever find life on Titan, we'll do it for a case of 2. But right now, case of 1, and then we keep our eyes open for anything weird, because that's going to be probably where even the more interesting discoveries are going to come from, things we can't explain, and that will start a whole new research area.
Thank you.
I'm David Allen. This is the third session in which we've heard how social taboos in the particular discipline have prevented data from coming forward. Important data that then eventually led to taboos, led to really breakthroughs. This may not be an existential crisis, and we see this kind of herd-following behavior very much outside of scientific disciplines. But today is about the undiscovered, and it's been operationalized as celebrating failure and the benefits of failure. In fact, this problem of taboos was addressed in the first session in talking about how do you grant tenure to somebody who's failed. Let's imagine that this is a problem of the social climate in a discipline, and as I said, also outside of scientific disciplines, but that's what we're talking about today. If you'd reflect in your own domain, and if you please, beyond that, in other sciences or even otherwise, how might we address this, what appears to be a problem if we're going to be serious about not keeping important data hidden?
I think one of the first things I would say is science is not never ever disconnected from the human endeavor, right? We are all humans first, and then we train as scientists. So there will always be this thing where we're like, oh, this can't happen. But then with enough evidence, we change our ideas. We say, okay, because other than that, we would have never done this discovery. Everybody would have pushed it under the rug. There's enough mounting evidence, then you say, okay, so my human intuition that this cannot happen is now overrode by my analytical training that I have to look at the facts. But science is a human endeavor, and it takes time for that to come through, I think.
Yeah, I'll just add to that I think this is a really serious question that you've raised. And in my mind, the best way to address it is by educating kids. I wish that every funding agency had the attitude that you have about risk-taking. But the reality is that we're accountable to our taxpayers, who often have who are taught a mindset about science that you have to have your hypothesis and test it. And so being uncertain and doing risky things and trying to explore the unknown is something that we're not very comfortable with as a society, I would say. And so changing the way science is taught so that the next generation of voters and taxpayers is more comfortable with this is, I think, what we should do. Looking at you, high school kids.
So human beings are our real topic. Thank you so much.
Laura and Lisa and Dave for that fantastic conversation.